Every second, thousands of aircraft cut through the world's skies, sustained by one of physics' most elegant applications, the wing. This seemingly simple structure harbors a universe of complexity. Within it, an intricate network of aluminum ribs forms the skeleton, while main spars distribute structural loads along the entire wingspan. The external surface creates the aerodynamic profile that generates the pressure difference fundamental to lift. Flaps, those movable devices on the trailing edge, extend during takeoff to increase the wing's area and curvature, amplifying lift at low speeds as well as during landing. Each movement is controlled by complex hydraulic systems, electric motors, and a network of sensors that monitor pressure, temperature, and position with millimetric precision. But however sophisticated this century-old engineering may be, it carries inherent limitations. Conventional flaps create abrupt discontinuities in airflow, generating turbulence that robs what aircraft need most: efficiency. A wing optimized for cruising at 560 miles per hour at high altitude becomes inadequate for takeoff at 186 miles per hour at sea level. It's like using the same tool for different jobs. It works, but never ideally. This technology, however, is about to change, and what you'll see in this video is already being tested right now and is about to transform everything we know as wing.
If you're also passionate about the world of aviation, consider subscribing to the channel and supporting our team.
Pay attention to this video. Did you notice something different about the wings? These are morphing wings or metamorphic wings, born from a simple premise: continuously changing shape, adapting to each moment of flight as birds have done for millions of years. This is not science fiction, but emerging reality in the world's most advanced laboratories. The fundamental concept remains the same. Airfoils generate lift through pressure difference between upper and lower surfaces. The revolution lies in the ability to optimize this geometry dynamically. While conventional flaps offer fixed configurations, retracted, partially extended, or fully extended, morphing wings provide infinite shape possibilities, adjusting curvature, thickness, and even twist in real time. This sounds a bit complex, so I will try to be very didactic. 3 technologies converge to make this possible. First, smart materials, shape memory alloys that remember specific configurations when heated, and macrofiber composites that respond to electrical stimuli. Second, revolutionary actuators, like ultrasonic motors operating without gears, and piezoelectric devices that convert electrical energy directly into mechanical movement. Third, adaptive structures that distribute deformations smoothly, eliminating the discontinuities that harm aerodynamic efficiency. Nature has always been the greatest engineer. Observing an eagle gliding in thermal currents, scientists noticed how its feathers subtly adjust to every change in wind. A shark's tail flexes with millimetric precision to optimize propulsion. These observations weren't merely aesthetic, they became the blueprint for a technological revolution. In the 80s and 90s, the first attempts to create morphing wings failed. Primitive control systems couldn't coordinate complex deformations, and available materials simply couldn't withstand the structural stresses of real flight. Prototypes broke during tests, hydraulic systems leaked, and the aviation industry remained skeptical. But scientific research persistence, fueled by advances in nanotechnology, materials science, and digital control systems, finally began bearing fruit in the 21st century. What was once impossible became not only viable, but extraordinarily efficient. At Swansea University in Wales, the fishback, or fishbone active camber system, represents a quantum leap in morphing technology. Inspired by a fish spine structure, the system uses 4 integrated components: a flexible carbon skeleton, pre-tensioned skin that maintains aerodynamic smoothness, tendons with pulley systems that distribute forces, and a rigid main spar that ensures structural integrity. Wind tunnel test results shocked even the researchers themselves: 125% increase in aerodynamic efficiency compared to wings with conventional flaps. Even more impressive, the system managed to significantly reduce drag while maintaining necessary lift. The wing's internal volume remained intact, preserving crucial space for fuel, a benefit that aeronautical engineers consider almost magical. At the University of Manchester, Rui Wu and his team developed a different approach, focusing on active trailing edge with multiple degrees of freedom. Using high-performance carbon fiber combined with actuators that convert electrical energy into movement through the inverse piezoelectric effect, the system offers granular control over each wing section. The initial prototype, manufactured via 3D printing for concept testing, demonstrated consistent improvements in lift-to-drag ratio across all tested morphing modes. The future version will incorporate linear ultrasonic motors, technology that eliminates gears and drastically reduces weight, operating with micrometer precision.
The NASA-MIT partnership resulted in a radically different approach, a wing formed by thousands of small reinforced carbon modules, connected like microscopic Lego pieces. The concept is audacious. The entire wing can be twisted uniformly using only 2 small motors positioned at the tips. The numbers are impressive. The system maintains the same aerodynamic performance as conventional wings with only 1/10 the weight. This opens possibilities for completely new aircraft designs, especially in space applications where every gram counts. The risk, naturally, lies in the multiplicity of failure points, thousands of connections that need to function perfectly under extreme stress.
The FlexSys and the NASA partnership generated even more promising data for commercial applications.
Their projections indicate fuel savings of up to 11%, a direct result of continuous aerodynamic profile optimization. Simultaneously, the power required to operate control systems reduced by approximately 20% compared to conventional hydraulic flaps. The U.S. Air Force Research Laboratory demonstrated practical viability with a radio-controlled model that performs rapid and independent adjustments on each wing during flight. Test pilots reported unprecedented control, especially in turbulent conditions. But perhaps the most surprising application isn't in the skies. Preliminary tests on wind turbines equipped with morphing blades demonstrated a 15% increase in captured energy, resulting from the ability to continuously optimize attack angle as wind direction and intensity change. The most comprehensive scientific review on morphing technology, published in 2024, published data from more than 50 laboratories worldwide. The results define new parameters for aeronautical efficiency, drag reduction of up to 25%, and control increase of up to 40%. To contextualize these numbers, a 25% drag reduction on a typical commercial aircraft equals eliminating the fuel consumption of approximately 50 passengers during a flight. But challenges persist on 3 critical fronts: certification, reliability, and cost. Global regulatory agencies are still developing protocols to approve systems that continuously change shape. How do you certify something that, by definition, has no fixed configuration? Reliability requires millions of morphing cycles to occur without failures, and current development costs still exceed economic benefits for mass commercial applications. The most recent evolution focuses on airfoils with variable camber and thickness, developed in 2024. Using systems of movable points connected by articulated rods, these designs offer real-time fine adjustment, ideal for UAVs. Applications in rapid maneuvers are especially promising. Modern fighter jets depend on large, heavy control surfaces to perform extreme maneuvers. High-frequency morphing can provide similar control authority with smaller surfaces, reducing weight and increasing agility. In transitional regimes, such as the transition from subsonic to supersonic flight, precise flow characteristic control can eliminate instabilities that currently limit performance. Beyond all these benefits, another particularly caught researchers' attention. By reducing drag with morphing wings, they also identified a noise reduction of approximately 15 decibels, sufficient to transform urban airports from noise pollution sources into tolerable neighbors. A surprisingly promising application is in aerobatic flying. Aerobatic aircraft operate in extreme flight regimes, including inverted flight, where conventional controls become counterproductive. Morphing surfaces maintain efficiency and control authority independent of aircraft orientation. Test pilots from the National University of Singapore, using prototypes with piezoelectric macrofiber composites, reported unprecedented control during inverted maneuvers. The system allows complete wing deformation, instantly adapting to inverted aerodynamic flows. Development and manufacturing costs remain prohibitive for commercial applications. A morphing wing costs approximately 300% more than a conventional equivalent. Operational benefits must justify this initial investment through fuel savings and reduced maintenance. We are on the threshold of a revolution that will redefine not only how we fly, but how we generate energy, explore space, and interact with moving fluids. Morphing wings represent more than incremental innovation. They are a paradigm shift comparable to the transition from sails to engines or propellers to jets. In the next 15 years, we expect to see the first commercial aircraft with partially morphing surfaces. The true revolution, however, will be conceptual. Generations of aeronautical engineers have thought in terms of compromises: speed versus efficiency, lift versus drag, stability versus maneuverability. Morphing eliminates these compromises, allowing simultaneous optimization of multiple parameters.